Hello, all of my hard studying students, and thanks for watching or thinking about watching another video. Indeed, this is a review of the important topics we have already talked about, but it's a review of electrochemistry stuff. So, what is electrochemistry? We start with redox, reduction and oxidation. Usually, the metal will give up its electrons to the nonmetal. Because metals like to give up electrons, nonmetals like to gain electrons. So metals like to get oxidized, nonmetals like to get reduced. It seems kind of backwards, doesn't it? So if you lose electrons, you're oxidized, but you're called the reducing agent, and vice versa. Like I said, there are many exceptions. Doesn't always have to be this way. Some metals can give up electrons, some metals can take on electrons, like the metal ion, silver ion. We'll get to that, I hope. Another cartoon for the same story. Likes to lose, likes to gain. Think about the electrons as something that's easily exchanged from one to the other. This is a nice thing to remember. Oxidation is a loss of electrons. Reduction is a gain of electrons. If you lose negatives, you become more positive. If you gain negatives, you become more negative in charge. Oxidation states. Do you remember figuring out oxidation states? We actually practiced it last term. But if you can see who goes down in oxidation number, you know it must have gone down because it gained negative electrons. Yes. And if the oxidation number goes up, you must have lost negative electrons. And we also talked about a scheme for balancing redox reactions, but more likely on the final that you wouldn't be asked necessarily to balance a redox, an unbalanced aqueous phase acidified redox reaction, but to check and make sure it is balanced. You might have to figure out oxidation numbers. Here the iodine in the -1 goes to the iodine in a +5 state, losing electrons. Chromium gains electrons. Oh yeah, and so why do we care about redox? Because it is the principle that batteries operate on, and the opposite of the battery, called the electrolytic cell. We said if you take two dissimilar metals, stick them into an electrolyte solution, there's a really good chance you can generate a potential difference. So if I had a copper and a zinc bar, stuck them into a lemon, I can get some kind of battery. The zinc gets oxidized, and you might say, well, the copper might get reduced, but in the true lemon battery, there's no copper ions. It's just the acid that gets reduced to hydrogen gas. And the idea is you can take two dissimilar metals, connect them up in two half cells, and the voltage is generated between them because the copper and the silver, say for example, have a different potential for being reduced or oxidized. In this one, it looks like what? Oh yeah, right. One electrode gains mass because the silver ion comes out of the water and gains electrons from the copper, and the copper electrode gets eaten away skinnier and skinnier into the water. We gauge all of these half reaction potentials relative to the standard hydrogen electrode, which is a contraption something like this, but it's hard to imagine because it's not common in the laboratory to see such a thing. Here's a zinc copper. No, my bad. Here's the zinc electrode in juxtaposition with the standard hydrogen electrode. Again, the zinc gets eaten away, goes into zinc ions in the water. The electrons leave the zinc electrode, travels through the meter, and over here where the electrons are gained by the hydrogen ions. Here's what's the difference here? Looks like they just switched it backwards. What? I apologize. So when we see big tables of reduction potentials, here's the key. The more positive the reduction potential, the more likely that reaction is to happen in the forward direction spontaneously. The less positive, if I were taking this half reaction, the less positive or more negative one, I end up flipping backwards. And so this one will be flipped backwards if I'm adding it to this one to get a full reaction. And I think we've illustrated that here a little bit. Although curiously, as I multiplied this equation, this half fraction by 5 to get 5 electrons lost to 5 electrons gained, I do not multiply this by 5. This is just referenced in the table relative to the other half reactions, reduction half potentials. In the last chapter, or the chapter we studied thermodynamically, we said there's a connection between the free energy, standard free energy, and the equilibrium constant. If we take that and equate that now to another equation for the free energy and the cell potential, and we might review that in a minute. I think my slides on that are a little bit lower down. We can get a good connection between the free energy and the cell potential and the free energy and the equilibrium constant. R is the gas constant in energy units, Faraday's constant, number of electrons transferred, Kelvin temperature. Interesting. And there's also another equation called the Nernst equation for non-standard cells. A lot of these standard reduction potentials are referenced relative to, let me go down, relative to hydrogen and relative to standard conditions, which we call, so this E naught comes from the table. When I combine one or the other, zoom in here a little bit, apologize, let's see. So I could say, yeah, I could say these half reactions are very likely to happen in the order given, and they're very positive in their reduction potential. And these are good oxidizing agents. They really want to happen in this order. Conversely, if I come down here, the ones that are low on the table and negative do not want to happen in the order given as reductions. They actually want to be flipped backwards. So lithium and cesium and potassium, rubidium, strontium and sodium are good reducing agents. They want to give up their electrons to reduce someone else. Here's the key, one of the keys. Oops, apologize. One of the keys is this. Again, the more positive the reduction potential, the more likely that reaction is to happen in the order given. So these are all going to want to happen in the order where I have the gaining of electrons. And you should know this. This will come in handy again and again. On the other hand, the elements at the bottom of the table, the half reactions at the bottom of this table list, are very negative in their potential, standard potential, and not likely to happen. And then again, these are all referenced relative to each other, and also 1 molar solutions if it's aqueous, 1 atmosphere of pressure if there's a gas, and room temperature, 25 degrees Celsius. So if I had wanted to try to make a battery from the chlorine bromine, it'd be the chlorine goes to chloride and the bromide goes to bromine. So I'd have to flip this one backwards as it's less positive. And I see my standard cell potential. If I had 1 molar bromide, 1 molar chloride, 1 atmosphere, oh no, goodness, that's a tricky one. 1 atmosphere pressure of chlorine and just a fixed amount of bromine liquid. Not fixed, sufficient amount, that's the right word. So if I want to make a battery from the iodine, copper 2 plus copper, can it be done? Well, yeah, they're different reduction potentials, so I'm sure I could take the one that's less positive and flip it backwards and get us some kind of positive battery. On the other hand, if I wrote this backwards and wrote this goes to this, that would be a negative 0.19 potential. Same story, even if they're both negative, take the less positive one and flip it backwards. So I took this one and flipped it backwards. Multiply by 2 and 3, but don't multiply those things. Or another kind of twist is you'd be given an equation that says, will this work? Can this happen? So I take my 10.2 plus, 10.4 plus, but that's written backwards as is given in my reduction potential. So I kind of wrote it backwards and changed the 0.15 to negative 0.5. And I left the lead 2 plus lead 2 plus lead like it was given, because I'm asking the question, can this serve as these reactants and these products? And the answer is no. This would not be a good spontaneous battery in the forward direction, because I came out with a negative cell potential. A different one where you would get a positive cell potential is this one, where I had the cadmium 2 plus cadmium and the calcium 2 plus equation written like this. Ask question, will I get a good battery from this? What's the standard cell potential? This one came out positive. Let's see. think I'm going to leave that for now. Have you reviewed the standard cell notation? Chromium electrode, chromium water, salt bridge, hydrogen ion, acid, hydrogen gas, platinum electrode. Alright, so back to the Nernst equation. These E0 values are referenced relative to the standard reduction potentials. But if I change the concentrations or temperatures, then I can change the cell potential. And so what? Faraday's constant, F, the gas constant in energy units, the Kelvin temperature, the number of electrons transferred, and Q is the reaction quotient, which kind of thinks about how much of one versus the other. At room temperature, that equation simplifies to this. And I think you're given this on the final, this equation. So this is kind of a weird one, where I have a copper here and a copper here, but this copper is 1 molar and this copper is 0.1 molar. This is a true concentration cell, where this would be 0 if I had the same metal, copper and copper. I don't get any standard cell potential unless I tweak with the concentrations. And if I always put the smaller concentration on the top of my reaction quotient, my logarithm comes out negative, so that the subtraction of the negative term ends up giving me a positive battery. Interesting. What would be the cell potential? I think we did this one in class too, so let me not review that one again, but it's on the PDF. Or alternatively, we can use electricity to force a chemical reaction, which is kind of a whole other can of worms. With molten electrolysis, it's pretty straightforward. The positive ion is forced to gain electrons, the negative ion probably forced to give up electrons. That'd be a dangerous setup. Half reactions look something like this. But if you're electrolyzing water or aqueous solutions, then the problem is the water always gets in the way. There's a possibility that water could give up electrons or take on electrons, get reduced or get oxidized. And if either of these are more positive or less negative than the other possible half reaction, then it's quite possible that the water would get involved in the story. So which is more positive, this one or this one? The answer is this is going to happen at this electrode of sodium, aqueous sodium chloride. Or which is more positive or less negative, the first one or the second one? And it looks like this one's less negative. So again, this one will want to happen. So if I try to electrolyze water, if I try to electrolyze sodium chloride, I'm just gonna get the water breaking down like this. And as long as I put about 2 volts into the mix, I'll be able to break that water down no problem. That's curious. So this is one of the only ways we have that we know of to easily break water apart. Okay, interesting. And 1 or 2 is more likely to happen. Less negative, I'll go with that one. And again, 1 or 2 is more likely to happen. Less negative is more likely to happen. So I'd see the iodide creating iodine. I would see the water breaking apart to make a base and give off hydrogen gas. Or again, 1 or 2 is more likely to happen. The more positive or less negative one. And again, 1 or 2 is more likely to happen. Looks like the less positive one's more likely to happen. So I can add those two half reactions together, get an overall equation. There's an equation you should memorize for the exam. It's moles generated equals current in amps times time in seconds divided by the number of electrons transferred and Faraday's constant. Memorize that one. Practice it a few times. It's really simple and saves you a lot of time if you're trying to answer these electrolysis questions, trying to decide how much of a particular compound could be created, how many moles plated, generated through electrolysis. I think I'm about out of time. Yeah, seriously, I think I gotta stop. Thanks, guys, and I'll see you in class. Have a good one. Good luck studying.